So this unit, again, Revolutions in Modern Physics, we're talking about the special theory of relativity section of this unit. And we're going to look at section 11.3. First, we're going to look at length contraction. And then afterwards, we're going to look at the other two topics, which are simultaneity and relativistic momentum. But when it comes to length contraction, this goes back to some of the strange implications of the special theory of relativity. So we've already talked about how time is relative, and time depends on the observer. So it's measured differently depending on the observer. As you go closer to the speed of light, what we call relativistic travel, we start to see these relativistic effects where time dilates. But there's another aspect of another physical constant, I guess, that will change, and that would be length. So how this changes, we'll get into in this lecture. So it says time dilation is only one of the consequences of Einstein's special theory of relativity. Since reference frames also involve measurements of position and length, there are also consequences that deal with space, such as the contraction or compression of length. So this image here kind of summarizes what we're saying. If this train was at rest, it would have a length of L. If it was in motion, it would have a shorter length, a length that would be affected, or rather the dimension that would be affected would be the one that is moving, or that is in the same direction as the motion. So its height and its width would not be affected, but its length would contract. As well as our changing understanding of time and length, special relativity also changes our understanding of momentum, energy, and mass. So if we have a change in length, that would also result in a change in mass, because our density our density would remain the same, but our object would be altered in terms of its volume. So we would then have a change in mass. Energy, or rather momentum, which is mass times velocity, would also change. And energy would change because our mass would change. So our energy equation for kinetic energy is 1/2 mv squared. If our m changes, then our energy changes as well. So there's relativistic effects with momentum, energy, mass, time, and length. So it seems really strange. All this stuff is kind of, all of these physical or measurements that we consider to be unchangeable or relatively constant in terms of our understanding now start to change as we travel faster and faster towards the speed of light. Now you might think that well, we can throw away all of Newton's equations and all of the other things we were studying because they don't work at relativistic velocities. However, they do work very well in the non-relativistic frames of reference. They're easier equations to use, so we do still use them. There's no point in adding in the changes due to relativity when those changes are going to be extremely small in terms of how they would affect time, length, mass, energy, momentum, and so on. So now let's get into a thought experiment to see how this happens. So we had the situation where we had the one observer who's on a train car that's moving with a constant velocity v, and another observer who is stationary with respect to that observer. The distance from A to B for observer 2 would be ls. We call that you'll see that's going to be called the proper length. Now, how would observer 1 measure this distance? So observer 1, he can measure the distance between A and B using a clock to measure the time, which is, in his case, it's his proper time. His proper time could then be used. So his proper time can then be used to determine how far he has traveled, because we know his velocity v. One thing to note here is that the proper time is the time of the person moving with the process, whereas the proper length is the length observed by the person outside of that process. So it gets a little bit different in terms of how we refer to these. So now for observer 1, his length would be measured relativistically as v times his proper time. Lm is his relativistic length. Delta Ts is the proper time. Now, that length will be smaller than the proper time length that is measured by observer 2. So this partly explains how the time to travel from A to B would be different. It's because the length between A and B has contracted as well. So when observer 2 measures with her clock how long it takes observer 1 to travel from A to B, the value she determines for her relativistic time is that proper time divided by that relativistic factor, 1 minus, or the square root of 1 minus v squared over c squared. So she has that delta Tm, her relativistic time. She would multiply that by the v to determine how far, what distance was traveled between A and B. And she will have an Ls that will be larger than the Lm of observer 1. So you can copy this down where it says proper length. So the distance for observer 2 is v times delta Tm, times her relativistic time, the time she measures. And that will be a longer length than the relativistic length. So looking back at our relativistic time equation, if we just multiply that by v, what we would end up with is our equation for relativistic length. So if we solve, v times delta Tm is equal to Lm, the relativistic length. V times delta Ts is equal to Ls, which is the proper length. If we then rearrange for relativistic length, we get Lm equals Ls times that relativistic factor, square root of 1 minus v squared over c squared. So because the relativistic time is different from the proper time due to time dilation, it only makes sense that the lengths measured by the two observers will also be different. So in this case, the length measured by observer 1 is shorter than the length measured by observer 2. So we call that length contraction. It's the shortening of the distances in an inertial frame of reference moving relative to an observer in another inertial frame of reference. So this is the spatial counterpart to time dilation. And again, length contraction only occurs in the direction of motion. So if we had a cylindrical rocket ship like we see here, if it is not moving, it will have a certain length. As it's moving at, say, 0.866 c, its length will contract to about half. As it moves closer and closer to the speed of light, its length contracts even further. However, its width and its height would remain the same. So please copy this down for length contraction. Sorry, I'm going to move that up a bit. It's the spatial counterpart to time dilation. So when we look at space-time, if the time is altered relativistically, then there must be some spatial component that has a relativistic effect as well, and it would be the length. I'd also like you to copy down that the length contraction only occurs in the direction of motion. So length contraction only occurs in the direction of motion. Okay, so let's look at some questions here. If the equation for length contraction is true, why have we not noticed it before? This is the same kind of question we had on the previous lecture. We don't notice it because we don't travel at relativistic speeds. So Lm over Ls for us is nearly 1. Technically, if in your car as it is driving and as it's moving at, say, 100 kilometers per hour, it's technically experiencing a very, very small length contraction. But we would not even notice that because the difference between the relativistic length of the car and its proper length when it's at rest is so close to 1 that we wouldn't even notice that there was a change in its length. So let's look at some problems that require the use of the equations here. So if we have a spacecraft and this spacecraft travels at 2 times 10 to the 8 meters per second, observers on Earth measure the length of the spacecraft to be 554 meters. How long would it be according to the passengers? So the observers on Earth would be measuring the relativistic length. So that means we have Lm equals Ls times our relativistic factor, 1 minus v squared over c squared. So we need to find out what our Ls is. So it's going to be Lm over the square root of 1 minus v squared over c squared. So this would essentially be what is the spacecraft's length at rest. So substituting these values in, I have 554 over the square root of 1 minus 2 times 10 to the 8 squared over 3 times 10 to the 8 squared. And I'll put this in the calculator here. 554 divided by, I'll need to put brackets, 1 minus 2 times 2 divided by 3 divided by 3. Here's an interesting thing. 8 squared divided, or 10 to the power of 8 squared divided by 10 to the power of 8 squared is going to be 1, so I don't need to do anything with that. I'm going to close this bracket, and I'm going to find the square root of this, and then I will hit my equals button. I end up with a length, a proper length. So if the spacecraft is at rest, it would have a length of 743 meters. Another concept that this question brings up that I didn't mention previously, even though there is length contraction of this spacecraft that is moving, the observers in the spacecraft would not notice the length contraction. So in their case, the proper length would be the length of the vehicle at rest. As it experiences that length contraction would only be noticed by an observer who is not moving relative to the vehicle. Here's another question. We have an asteroid. It has a length of 725 kilometers. A rocket passes by parallel to the long axis at a speed of 0.25 c. What will the length of the asteroid be as measured by observers in the rocket? So the asteroid has a proper length of 725 kilometers. The observers in the spacecraft will observe its length at a relativistic length measure. So if we substitute these into the equation, we end up with 0.250 squared. So this becomes 725 times bracket 1 minus 0.25 times 0.25 Close the bracket and square root that. I get 702 kilometers for my relativistic measure. So those are the observers in the rocket. They would measure it at that length. Here's another question. We have a spacecraft that is spherical. It's a spacecraft that passes a spherical space station. Observers in the spacecraft see the station's minimum diameter as 265 meters, and the maximum diameter is 325 meters. So that maximum diameter is the diameter in which they are not moving in. It's the direction that they're not moving in, so it's perpendicular to their direction of motion. The minimum diameter is the diameter of the direction in which they are moving in that motion. So how fast is the spacecraft traveling relative to the space station? So here we have to solve for v. So we know the LM, the relativistic length, is 265 meters. The LS, that diameter at rest, is 325 meters. So how do we solve for our v? So this requires some of your algebra skills here. We write down the equation in its usual form, and then we have to isolate for v squared. So LM over LS, I will square this. This is going to be 1 minus v squared over c squared. And then if I want to write this for v squared, I have to move the 1 to the other side. So I'll do this in a few extra steps here just so that you can fully see what's going on here. So now I have minus 1 equals minus v squared over c squared. To get rid of this minus, what I'm going to do is I'm going to multiply both sides by negative 1. So every term is going to be changed in terms of its sign. So I have, instead of this minus 1, it becomes 1. Instead of this being positive, it becomes negative. Equals v squared over c squared. I'm then going to swap the sides because I want to have my v on the left side. And I will multiply this side by c squared, and I will square root everything. So under the big square root, this will be c squared 1 minus LM over LS squared. So now I can substitute in. And over here I have 1 minus 265 over 325 squared. Write that really small there, but okay. So now c squared is going to be 9. Let me put brackets first. 9 times 10 to the power of 16. I'll have to multiply this by another bracket, 1 minus another bracket, 265 divided by 325. I'm going to close that bracket, square that term, close that bracket, and multiply, those are multiplied together. So I can close this bracket again and square root. Something went wrong there. Let me do this again here. So I have 9 times 10 to the power of 16. Oops. 9 times 10 to the power of 16 times 1 minus 265 times 265 divided by 325 divided by 325. Close that bracket. So I have, that's basically what's, I have to press my equals button. This is what's underneath my square root. And then if I square root that, I get 173, let me put this in scientific notation, 1.74 So V equals 1.74 times 10 to the 8 meters per second. That's how I would solve for my V. This question continues. It says, why does the spacecraft not look like a sphere to observers in the spacecraft? Well, because of the length contraction, it's basically turned this into an ovaloid. The length contraction occurs in the direction of motion. Okay, now we'll look at some evidence for length contraction. So length contraction seems pretty strange, but when we work with small particles that move at relativistic speeds, we can actually notice length contraction. So the decay of unstable elementary particles called muons demonstrate how length contraction and time dilation complement each other. One source of muons is the cosmic radiation that collides with atoms in the Earth's upper atmosphere. According to Newtonian mechanics, most of these muons should decay after traveling about 660 meters into the atmosphere. Yet experimental evidence shows that a large number of muons decay after traveling 4,800 meters. That's 7 times as far. So why does this happen? It explains here in the note that muons are particles that are about 207 times as massive as electrons. They travel at about 99% of the speed of light, and they decay in 2.2 milliseconds for an observer at rest relative to the muon. So because they have that 2.2 milliseconds lifetime, the fact that they're traveling at 99% of the speed of light means that they would exist for longer, which means they would travel for a longer distance. So the only explanation for why these muons can travel that far is from special relativity. The muons' clocks run slower relative to the Earth's clocks, so they would travel a farther distance. It says, what would this situation look like from the muon's frame of reference? So the muon would actually still have a lifetime of 2.2 milliseconds for the muon, even though it has this relativistic time that it experiences. And it would still only travel 660 meters, even though relativistically it traveled 4,800 meters. It's the fact that the distance it traveled was contracted. So you can copy this down for length contraction as well. Some other notes. You may want to copy that note as well at the bottom where it talks about the muon's point of view. I know this is pretty strange, hard to understand. Just stick with it. I'm sure you'll get it if you're having trouble. And if you have any questions, feel free to ask them on the course website.